All right. So hi, everybody. My name is Nick Spooner. I'm a PhD student here at, well, not literally here, but down the street at UC Berkeley. My advisor is Alessandro Chiesa, whom a lot of you surely know. And today I'm going to be talking with Dev about a protocol that we have called Aurora, which gives you transparent ZK snarks for rank 1 constraint systems. Dev is one of our implementation guys, so he's done a lot of work on making the Aurora implementation work. So he's going to be talking a little bit at the end about the system and how that works. And I will be talking about the theory stuff. OK. So everyone, hopefully by this point, knows what a zero-knowledge proof is. I guess the definition has been given 15 times today, so I'm not going to give it again. Instead, I'm going to talk a little bit about, and this was actually mentioned earlier, about how you build a zero-knowledge proof in general. So we start with a statement that we're interested in, which is usually represented by a circuit or a machine or a program, some computational model that's easy to write statements in. And then we do a reduction to an intermediate representation, which in general looks very different to the statement that we started with. So maybe it's some routing problem on some structured graph, or maybe it's something even weirder, like a domino tiling, something that's NP-complete. And then we take this problem, this kind of proof-friendly intermediate representation, we pass it to our proof system, and the proof system outputs a proof. So I'm going to call the reduction part the front end and the proof system the back end. And in between these two things, we have this intermediate representation. And what I want to impress upon everybody is that the intermediate representation is very important. So the proof system can be as efficient as you like. But if your intermediate representation is bad, if your reduction introduces a large overhead, then your proof is not going to be efficient in the end, right? This whole composition is going to be slow. So with that in mind, I'm going to talk about one particular intermediate representation, which you have seen many times today already, which is rank 1 constraint systems. So what is a rank 1 constraint system? Well, in case you've forgotten over the past hour, you're given a public input, which is 3 matrices. A, B, and C, and a vector X, and all of these are over some finite field. And then the problem is you want to check whether there exists a secret vector W such that if I take X and W and I concatenate them together to make this vector Z, is it the case that AZ times BZ equals CZ, where this thing in the middle here is the element-wise product, or if you're not familiar with that, the Hadamard product is also what it's called. And this is going to be our intermediate representation, right? So we're going to reduce our problem that we want to actually prove things about to some R1CS instance and then output a proof. So what is nice about R1CS? Well, the first thing is that if you have an arithmetic circuit over this field, then it's very easy to move from that representation to the R1CS representation. So there's a linear time transformation that gives you an R1CS instance. It's very simple. And the other nice thing about it is that unlike this arithmetic circuit I started with, we have this really nice, simple linear algebraic structure to work with, right? So we have just these matrix multiplications, matrix vector multiplications, and this element-wise product. And finally, it's got some kind of demonstrated practical usefulness. So all of these systems use it. And kind of one of the reasons that we are all gathered here today is to discuss the possibility of making this a standard for zero-knowledge proofs. So this seems like a very relevant thing to be targeting. And it has a lot of advantages. OK. So like I said, this is the intermediate representation that we consider. And so Aurora is a transparent ZK snark for R1CS instances. So I will, if the clicker works, there we go. So I will explain firstly some of the nice things about it. So it has a very small argument size. The size of the argument is log squared in the number of constraints, or the number of gates in the circuit that you started with. Come on. There we go. We only use symmetric key cryptography, so this is in contrast to other things like either you may have seen like bulletproofs or pairing-based snarks. So the only thing that we need is essentially strong hash functions. And in particular, there is a proof of security in the random oracle model. And this security is unconditional in the random oracle model, and this means that the protocol has only trusted setup. Sorry, not trusted setup, only transparent setup, public setup. And one bonus that you get is that it's post-quantum in the sense that we don't know of any attack that you could mount using a quantum computer, apart from the kind of trivial Grover search-based type things. Okay, and what's more, we've implemented the system and evaluated it. So here are some numbers, and Dev will talk a little bit more about what, like, with the actual evaluation and the implementation later. But just to kind of give you a primer. So we get an argument size which is, for circuits with a few million gates, we get an argument size which is something like 50 to 150 kilobytes. Prover time is on the order of minutes, and verified time is on the order of seconds. So in particular for circuits, so for R1CS type things, the proof length beats Stark and Ligero by an order of magnitude, and we'll see that later with some graphs, which means that Aurora is the shortest symmetric key ZK snark for circuits. Okay. Unfortunately, if you really want short proofs, then you need to ditch symmetric key cryptography. So for bulletproofs, I mean, you can get proof sizes for the same kinds of circuits, which are smaller than 1 kilobyte. So the message is, if you can afford to if you can afford to make cryptographic assumptions, like use like public key crypto, then you can do much better than this. Okay. So how do we build these proofs? Well, I'm going to take a little historical tour for a moment and go back to the first ever constructions of snarks, which was due to Sylvia Macaulay in 1994. So he called them CS proofs, and what they are, you just have a prover and a verifier, and they both have access to the random oracle and this snark, right? And these proofs that you get, these have some very nice properties. So they have public setup because you only have the random oracle. They require only kind of lightweight cryptography, right? Again, the random like this is unconditionally secure in the random oracle model. And the post-quantum security with a little asterisk. So that's all great, right? These are all very nice properties, so long as you like random oracles. And so the question is, where do they come from? And the answer is this wonderful mathematical object called PCPs. So a PCP is just a proof string where the prover writes it down, and the verifier looks at the proof string in a few places and decides whether to accept or reject. So these are very beautiful things, but they have a lot of problems when we want to actually use them in practice. So asymptotically, the size of what you really want is linear sized PCPs. This is as short as you can go. But we don't know of any of these with small query complexity, right? So the best that we know is like enter the epsilon query complexity. Really, we want something which is polylogarithmic. And practically, the situation is even worse because we just don't have any efficient constructions of PCPs, even without zero knowledge. If you want zero knowledge, things get even worse than this. So this is unfortunate. And so what we're going to try to do is we're going to say, OK, this makes us sad, but we want to construct this same thing on the right that made us happy from something on the left that also makes us happy, right? And so the point is that we don't need to start from PCPs. PCPs are one thing that we could start from, but we could also start from something a little bit more general, and this is called an interactive oracle proof, or IOP. So what is an IOP? Well, it looks a bit like this. You have a multi-round protocol. The verifier sends a challenge. The prover sends back a PCP oracle, which the verifier is allowed to query. The verifier sends back another challenge, the prover sends back a PCP oracle, and you can continue like this as long as you like. And then at the end, the verifier makes a bunch of queries to all the PCPs, and then he decides whether to accept or reject. OK, what are the nice things about this? Well, so in terms of asymptotics, we can do better in this model than we know how to do with PCPs. So we can get truly linear size IOPs. This is for circuit SAT. Concretely, we have these efficient implementations. So this is work by Benteson, Bentov, Horesh, and Ryabzev. 2 different papers with the same acronym. And they show that you can actually kind of implement these things concretely in a way that is efficient for practical computations. OK. So that is great. So this is what we're going to do. We're going to design an IOP for R1CS, and then we're going to use this transform that was this blue arrow in the last slide to produce a snark. So here's the theorem. This is the only theorem. So there is a log n round IOP protocol for R1CS, which is a zero-knowledge proof of knowledge, with the following parameters, where n is the instance sizes, the number of gates. So what do we get? There we go. So we get a proof length, which is optimal. This is linear proof length. We have log n query complexity, which is pretty good. Prover runtime is almost optimal. It's up to a log factor. And the verifier runtime is optimal also. So it's the cost of the verifier is not much more than the cost of just reading the circuit. And all of this stuff is in terms of field operations, right? So if you cared about bits, you'd have a log f. All right. So it's important when we're talking about about proof systems to decide like what we're trying to prove things about. So this IOP and the resulting snark will all be about proving statements about circuits. There are other proof systems which prove statements about machines, such as Stark, which we'll mention a bit later. And these proof systems, they have very different properties, and whether you want to use one or the other depends on what your problem looks like, right? So these correspond kind of naturally to the complexity classes NP and Next, but you don't have to worry about that. Just think about circuits and programs. OK. So what is a program? Well, you're given a machine description, which is like a constant size thing, and you're given a time bound, and you say I'm going to run my program for t steps and check whether it says yes or no on my input x. A circuit, on the other hand, you're given a bunch of gates, and they're kind of explicitly written out with all the wires in between them, and you plug in your input and you see what comes out. Okay? So the difference between these two things is in the size of this statement. So here on the left, the size of the statement is the size of the machine description plus log t. And the size of the machine description generally we take to be constant, so this is really just log t. On the other hand, the circuit model, the size of the statement that you're trying to prove is the size of the circuit. Like you've written down the circuit and you've given it to me. On the other hand, the computation size, in the case of the machine model, is exponentially larger than the statement size, right? So here I have a log t, here I have a t. In the circuit model, the computation size and the statement size are the same. And this is important. Okay, and what's the difference really? The difference is that in the machine model setting, the way that you look at your computation is repeated applications of some transition function, right? So the machine model has repeated structure that you're exploiting, whereas the circuit model does not have any structure whatsoever, right? So the circuit model, you're given an arbitrary circuit, and there's nothing you can really, you can't compress it in any way. Which means that the challenges in both cases are different, right? So in the machine model, what the challenge is having a succinct proof and a succinct verifier, right? You want your verifier to run polynomially in the size of the statement and not the size of the computation. And there's an exponential gap. Whereas the challenge in the NP setting, well, we can't hope for a succinct verifier because it has to read the statement to begin with. And so what you want is you want to the challenge is producing a succinct proof, even though you have no structure to work with. So just to like make this very clear, the statement size is a lower bound here on the verifier running time. We're assuming that there's no pre-processing step. This is the model that we're working with, which means that in the machine model, the succinct verification is possible, whereas in the circuit model, it is not possible, unless you do pre-process. OK. So a little bit about the way that the Aurora protocol is designed. I don't have so much time, but I'll be able to say a little. So the goal is to design this IOP protocol with the following parameters. So you have short proof length and logarithmic query complexity. And so what do? I take my R1CS instance. And for us, the field is going to be fairly large, like larger than the size of the problem. And I can think about like a simple proof system for this R1CS instance. So the prover just writes down the witness, sends it to the verifier checks. OK. Now, if now what I can do is, this will seem a bit strange, but I'm going to break it down into 4 different parts. Right? So there are 4 equations that I have to check, really. I have to check, so I'm going to introduce these new vectors A, B, and C. And like A is supposed to be equal to A times Z, B is supposed to be equal to B times Z, and C is supposed to be equal to C times Z. And then at the end, I take all of these things, and I do this element-wise product, and I check that A element-wise product B is equal to C. So it shouldn't be hard to see that this is the same as the original protocol, as the original, R1CS problem, just written out in a strange way. And these things up here, I'm going to call these lin check because they're kind of linear like matrix vector multiplications. And this is called row check because it's a kind of row-wise property, right? So I check each element in the vector, I multiply the 2 together, and I check whether they. Okay. And so here's an alternative, very stupid proof system for R1CS, which is I send W, and then I also send A, B, and C. And then the verifier just checks all of these properties. OK. So this will start making sense once we look at the RS encoded version. So now I'm going to take all of these like A, B, C, and Z, and I'm going to encode them as univariate polynomials, and I'm going to write them down. So here's my original constraints. And what these turn into is the following things. So this, if I interpret this as a constraint about the encoded vectors, then it looks like this. And I have similar things for A, B, and C. And then this one, which is very simple, is just saying that the product of each of these in every point in H is the corresponds. So don't worry too much about what these exactly are. They're just kind of the equivalents of these statements just in the Reed-Solomon encoded world. And then separately, I need to check that this FZ actually encodes X correctly. OK. So what do? Well, so now that I've split this up into lin check and row check, I can check these things separately. And for row check, there are standard PCP techniques that allow me to reduce this to low degree testing. On the other side, for lin check, we need to introduce a new primitive called univariate sumcheck, which allows us to check lin check constraints. And this is what univariate sumcheck looks like. So you may have seen multivariate sumcheck before. This is just the univariate equivalent. You're given like oracle access to a low degree polynomial, and you want to check whether this sums to 0 over some set H. In order to do this without any help, you can prove that you need size of H queries. And what we do is we design an IOP protocol which reduces this exponentially to log of size of H queries, so long as H has algebraic structure. It has to be a subgroup of the field. OK. So I'm going to end the theory part with a couple of open questions, and then Dave has 5 minutes to talk about the, the system. So firstly, so I said in the previous slide, we have this protocol for algebraically structured sets. Can you do the same thing for arbitrary sets H? This would be very interesting. And And secondly, kind of the bottleneck in a lot of these things is the quality, but like the efficiency of the LDT. And so can you produce, can you design a better LDT is a very central question in all of these IOP-based proof systems. So this one and also Stark kind of suffers from the fact that we don't understand these things very well. OK, all right. Now I'm going to hand over to Dave.
Thanks. I'm Dave. So for the last several months, I've been working on this library for IOP-based ZK snarks, aptly called libiop. And as of yesterday, hey, it's now online, so you can go find it. It's MIT licensed, so you can use it for whatever you would like. And so I'll talk a bit about what's in the library. So I mentioned it's a library for IOP-based snarks. So you start with an IOP. Then we're going to compile it into a snark. So this is done via the BCS transformation, which Nick mentioned a little bit about. And so this is implemented as its own module, so you can compile any IOP you build. And then IOPs typically consist of two components, or at least the IOPs we have so far. An encoded version and some sort of low-degree test. So like this encoded version is where we restrict the prover to only being able to talk about low-degree polynomials. So this is like the Aurora protocol Nick was mentioning earlier falls into this. And then you combine that with the low-degree test, so the verifier is convinced that the prover did actually only send low-degree polynomials, and this gives you an IOP. So we have infrastructure for both these components. So in the library, we implement Aurora and Ligero. Oh, Stark is something that also falls under encoded IOP. And then we also implement the direct LDT and Fry. And we have these protocols all implemented for additive and multiplicative fields, or more precisely, like binary field extensions and smooth prime fields. And with, these also can be ran on a non-ZK mode for better efficiency. So since we have code, we can see concretely how it performs. So here's the argument size for these three protocols. The Stark comes from the open source implementation from libstark. We don't implement in the library. So this black line is Aurora, and we see that it's log squared and has the smallest argument size. This is expected because it targets R1CS explicitly. Whereas for Starks, they're in the machine model, so you have the simulation overhead for running R1CS. And then Ligero in the paper, the Ligero construction has a square root n argument size, n being the number of constraints. So we see that the implementation follows that as well. And then we can also see the verifier time. So we see that they all run fairly well, fairly fast. And they're also all linear because, as Nick had noted earlier, they all have to read the circuit. So you can't hope for anything better than linear. And thank you. If you have any questions, feel free to ask.
Thank you very much.